This is part 2 of the decision structures chapter video, and we will resume where we left off, talking about if-else-if flows. Again, just to briefly review, this is a complex structure that allows you to skip over other checks, almost like a sieve works. So it's like you're sorting through in this case, the F grades, the D grades, the C, B, A, and this is what that looks like in code. You may not be using this kind of structure anytime soon, but it's good to know that it can be done in Java in case you need to do something like this. And this is what it's useful for. We're going to move on to logical operators. So we've covered arithmetic operators in an earlier chapter. Arithmetic operators, of course, do the types of arithmetic you're used to: addition, multiplication, division, and others. And arithmetic operators operate on operands like integers, ints, in Java. However, logical operators are operators that take Boolean values as their operands. So there are two binary logical operators that are called and or that are used to combine Boolean expressions. And if you've ever done anything with digital logic, you're familiar with and or just other type of logic. That's why these are called logical operators. They mimic the and or of logic. There's a unary operator as well that negates or reverses the truth of a Boolean expression. Here's how they work. The two ampersands mean and. They combine two Boolean expressions into one. Those could be Boolean expressions can be a single Boolean value or the result of another Boolean expression. If both of the operands on either side of the and are true, then the overall expression has the value of true. And that's the way and works. So if both are true, then if both sides are true, then the entire thing is true. Or works a little bit differently. And if you're not familiar with logic, it may be a little bit unexpected. It may be different from the way you use the word or in everyday life. Or connects two Boolean expressions, but the overall expression will be true if at least one of the expressions that are the operands are true. So if A and B were Boolean values on either side, and you had A or B, if A is true, the entire expression is true. If B is true, the entire expression is true. If A and B are both true, then the entire expression is true. It would only be false if both A and B were false. So not is a unary operator, and it reverses the truth of a Boolean expression that comes right after it. In the previous example, we had A and B that were Boolean values. So if A is true, then not A would be false. So that's the most simple of the logical operators. We understand how our logical operators work through the use of what we call truth tables. So they're called truth tables because they show the cases where an expression will be true or false based on the operands that are the parts of the expression. So here's an example. You see expression 1, you can think of it as the leftmost operand, and expression 2, or the rightmost operand, and how they combine using the and operator. So if you've got a true and in the case of and, if you've got a true and a false, then that expression together is going to be false. False and true, that expression is going to be false. If you've got false and false, then the overall expression is false. True and true, the overall expression is true. So the only case in which it's true, in the case of and, is if both operands are true. Yep. Okay. So in other words, you would think of that if this and that are true, then the entire thing is true. Trying to think of an example. If your car needs gas and you have money for gas, then it's true that you can buy gas, for example. Okay? So before you buy gas, you need to check A, does the car need gas? B, do I have money for gas? Yes, the car needs gas. Yes, I have money for gas. Then yes, the entire expression is true. Okay? If either of those are false, then the thing evaluates to false. Okay, do I need to get gas? Well, only if I need gas. If the car needs gas and I have the money. Does the car need gas? No. Then it doesn't even matter whether I have the money or not. I'm not going to buy gas because the tank's full. Okay. Do I need gas? Does the car need gas? Yes, true. Okay. Do I have the money for gas? False. No, then I'm not going to buy gas. See how that works? Okay. And you can find those examples. Find for any situation that you have an and combination going on in the logic of your program, you can look at a table like this to see what the consequences of a true and a false on either side will produce. The OR operator has a different pattern. So I want you to notice the patterns here. So this, in the AND operator, it's true in one case and false in all three other cases. In the OR operator, it's a little bit different. It's false in only one case and true in all the other cases. So if expression 1 is true and expression 2 is false, the whole thing is true. Again, if either of the sides is true, then the whole thing is true. But even if both of the sides are true, then the whole thing is true. But if both sides are false, the thing is false. So, for example, let's say you're having a party and you want to decide if you need to go to the supermarket, and your friends really like chips and dip. So you are going to go to the supermarket only if you need chips or dip. Okay, so do you need chips? Yes, true. Then it doesn't even matter whether you need dip. You're going to go to the supermarket anyway. So if one of them is true, it doesn't matter what the other is. The whole expression is going to be true. Do you need dip? Then yes, you're going to the supermarket, because whether you need chips or not, the whole expression is true. Do you need chips and dip? Yep, you're obviously going to the supermarket in that case. That's the bottom case here. True, true. True, you need chips. True, you need dip. Do you need chips? False. No, you don't need chips. Okay, well, do you need dip? Nope, that's false. True also. So the whole thing evaluates to false. And that's the way OR works. Not is very simple. It just negates the value. Okay? It allows you to reverse a condition for the purposes of making your if statement work correctly. So, for example, if your conditional is checking whether the temperature is over 100, okay, then if you say, so is temperature over 100? This is going to be true when temperature is over 100. What if you want to know when the temperature is not over 100? Then you would say temperature is, you could say, one way to do it is to say temperature is over 100 and negate it. So temperature is not over 100. As I said before, there are cases where when you're evaluating something left to right, it doesn't matter what comes later if the truth or falsity of part of your a part of your expression causes the rest of the expression to not make a difference. That's called short circuit evaluation. For instance, the logical AND will evaluate to false as soon as the first operand that it encounters is false, right? So two things can't be true if the first thing is false. Therefore, we don't even check the second one. The OR will evaluate to true as soon as it sees that one of its operands is a true expression. So again, if you know you need chips, then you don't even have to check whether you need dip, because the entire condition is true. The expression is true. So you know you're going to go to the supermarket. Okay. Why is this important? It's important because sometimes when we are programming, we put things in an expression that can't be evaluated or that might cause an error in some cases, but it's safe to put them there as long as the left-hand side of the expression evaluates to true or false depending on the kind of condition that we are are building. And that's best shown or talked about in person. So I'm going to move on to order of precedence. So just like we have order of operations, precedence of operations in arithmetic operators, the logical operators have their own precedence. The negation operator has a higher order of precedence than the AND and OR operators. And the relational operators are part of this system as well. The AND and OR operators have a lower precedence than the relational operators, like greater than or less than. But of course, just as in arithmetic operation, you can use parentheses to force the order of operations that you want. So you always have that control using the punctuation. Now, here's the order of precedence shown all together in one chart. And the reason this is important is you're going to find that in Boolean expressions, they may be actually made up of some arithmetic expressions as well in there. So that's why we have this order of precedence, with the arithmetic operations having the higher precedence, because you can't evaluate a Boolean expression until the arithmetic operations within it are completed first. Okay? Let's see. So for example, if you're multiplying 5 times 2 and you want to know if that's greater than 7, then you have to do the multiplication of 5 times 2 first. That's multiplication here, the multiplication operator, before you compare it to 7 with the greater than symbol. Integers aren't the only things that can be compared. String objects are also necessary to compare for many different purposes in a Java program, but they can't be compared using the same operators because a string is a different sort of object. It's not a primitive, and for more complex classes, often the definition of what a comparison is malleable, or it can change in different situations. You need flexibility. But there are actually ways built into Java to do alphabetic string comparison. You're not actually comparing the string variable with another string variable. When you compare string objects, you're going to call a routine that is going to run an algorithm that does a kind of alphabetic comparison between the two strings. If you tried to compare strings directly, like the string variables, what it would be doing was it would be trying to compare the reference to the string, which isn't going to make sense in your program. So the commands the methods in the string class that allow you to do comparisons have names like equals and compare to. And these comparison methods are case sensitive. So one string does not equal another string if the case is different. That's because it's doing a character-wise comparison. So Java allows us to do case insensitive comparisons if that is our if that is what we need. For instance, if you're comparing user input and one user, you want to know if somebody's name is John. Someone types in John with a capital J and someone else types in John with a lowercase j. For the purpose of our program, we may decide that we don't care if it's been capitalized because we don't know, we don't force the user necessarily to capitalize their name. But we do want to consider John to be the same name whether it's capitalized or not. Then we would want to do a comparison using equals and we would want to ignore case. So there are examples of this in the book. Okay, scope is very difficult to discuss in a video, so I'm skipping over that for the moment. I'm also going to skip over the conditional operator. It's a shortcut operator that lets you do something that's like an if statement. I encourage you to look for it in the book if you're interested in it, but we will not be using it in class. A switch statement, on the other hand, is something that we'll be using in class, and it's like a built-in, more complex and sometimes more useful version of an if-else. Okay? In the if-else statements, of course, we are only allowed to tell whether something is true or not and to make a determination of what code we want to run if something is true and what other code we might want to run if that something is false. But a switch statement gives us the possibility of choosing a number of options depending on the value of whatever the operand is, whatever the parameter is that we are checking for that statement. Switch statements evaluate integer types or character types. There are other versions of languages, and Java is included in that, which sometimes will accept other types of variables in their switch statements, but we're going to confine our programming and our investigations to using integers and characters in switch statements. And here's what one of those things looks like. Okay, we say, so the switch statement starts with the keyword switch, then we have an expression, and that expression must evaluate to something that the switch statement expects, for example, an integer. So some expression that evaluates to, let's say, an integer value, or it could be a character, but in this case, let's call it an integer. In the body of the switch statement that is delineated by our curly braces, we can see that we have a number of cases depending on the value of switch expression. So for instance, let's say switch expression is an integer. So some integer, some int, we're going to switch on it. We're going to decide which case to execute. So what we would have is each case expression in the case would have a different integer value. So for instance, let's say you have, in this case, we have two cases. In this switch statement, we have two cases. So let's say the two cases are the numbers 5 and 7. So switch expression, let's say switch expression could possibly be 5 or 7. Then case 1 would be case and then the number 5, and then case 2 would be case and then the number 7. The format of one of the cases in a switch statement must be of this type. It must be the word case, the keyword case, the expression, so in this case it could be the literal 5, for example, a colon, and then one or more statements, and then the word break with a semicolon after it. And then you have the next case that follows. So you might have case 7, colon, a number of statements, and then the keyword break, and then a semicolon. Okay, well, then there's this default that you can place into a switch statement. The default is kind of the catch-all condition in case you don't get a 5 or a 7. So if you have a default in place, then if your switch expression here happens to not be a 5 or a 7, if it's an 8, it will check all the cases. Case 5, no. Case 7, no. And then it will go to the default, and everything else will fall into that. Okay. Okay, the break statement is important because each case must end in a break. The break statement allows us to differentiate our cases. Now, as you see here, according to the compiler, the break statement is optional. So if you understand how it works, you'll be able to use the break statement to change how your cases execute. Because if a case does not contain a break, then program execution is going to continue to the next case. I will show you an example of this in class, but right now understand that you won't get an error if you don't have a break statement in your case. That's what it means when this says that it's optional. It may not be optional for your purposes. It's optional according to the compiler. So it's up to you to understand what happens when the break statement is there or when it's missing, because the compiler is not going to warn you that a break is missing. Okay, we're skipping over printf for the purposes of this video. That will be part of our Chapter 2 discussion. This video is also not going to discuss decimal format, and so this video has come to its conclusion. Please, if you have any questions that are not resolved by rewatching part of this video, if you have anything that you noticed that you want to make a comment on, that you want to talk to me about, please make a note of it, bring it to me, bring it up in class. It could spark a very productive discussion. Other people may be wondering the same things. Decision structures are the first complex aspect of programming that we encounter in this class, and they are certainly complex, and they'll stay with us, and they will be useful, but also a source of things to think about. If you have any questions, make note of them, bring them up in class, or after class, or in email, and I will see you in class.